Okay, so we've discussed some of the we've introduced some of the basic concepts behind electronic cooling and the need for thermal management. This subset of Chapter 1 is just the basics of heat transfer, and we'll go into these in more detail in the next few chapters, but this information will form the basis of what we're going to talk about. So just a review of the temperature scales. This is a nice chart that shows, so we have, everybody's familiar obviously with the Fahrenheit and the Celsius scales, and then we have what are called the absolute temperature scales. And so whereas Celsius and Fahrenheit had their basis or their foundation for their temperature scales were developed at a time when physics, thermodynamics wasn't as well understood, and so the bounds of those temperature scales were based on physical phenomena. For example, Celsius, 0 degrees C at sea level atmospheric conditions is where water freezes, pure water, and then 100 degrees C is where it boils at. In contrast, for the Kelvin and Rankine scales, so Kelvin is, these are the absolute temperature scales, their basis, their foundation of 0 is absolute 0, where energy and motion ceases in matter, and it's never been achieved, although different techniques have been used to get down to extremely cold temperatures, very close. In fact, I don't know what the record is right now, but last I saw there was somebody that was achieving, I think, 4 decimals, getting close to absolute 0.0001 Kelvin, might have been smaller than that, and they were actually using pulsed laser light on individual atoms to get them to slow up. And imagine having a ball rolling around inside a box, and you're using your hands to restrict its motion and to slow it down every time it hits. That's what these lasers were doing, was pulsing these individual atoms and getting them to slow up and to stop their spin and motion. And as they do so, they lose out all their energy. And so they're using photons of light to actually exchange momentum and to decrease the energy. Anyway, for most of what you do in calculations associated with heat transfer, using the English or the metric temperature scales are fine. When we start talking, though, about radiation heat transfer, it's nonlinear. Yeah, you need to use one of the two absolute temperature scales. Okay, just some real basics. I'm sure you guys, based on your work experience and your education, are familiar with this. Energy flows from high temperatures to low temperatures, the net flow of energy. And the analogies are water flowing downhill or electricity flowing from high voltage to low voltage. So there are 3 modes of heat transfer that we use in electronic cooling. Radiation, which is the least common. There are particular cases where radiation becomes important, but this is a mode where energy is exchanged by electromagnetic waves. No intermediate medium is required to move the heat. So where would we find that radiation heat transfer may be significant for an electronic cooling case? Any ideas? Actually, in some of the things I've worked on, spacecraft instrumentation, it becomes actually a fairly significant contributor to moving the heat off of electronic components, because you lose one of the other modes, the last one, which we'll talk about in just a second, convection heat transfer. But for the majority of things that ground-based systems, where you're using air cooling, liquid cooling, radiation is fairly minimal. It's a very complex subject. There are computer codes that handle it. They're fairly intensive in the computational time if you include radiation heat transfer in your analyses. So based on what I understand on your backgrounds and what you're doing, I'm not going to talk too much about it. It's in chapter 5. We'll just barely touch on it. Radiation is an extremely tough subject to understand. My expertise is in heat transfer. That's what I studied in my master's and my PhD work. And I actually took a PhD course in radiation heat transfer, and from one of the world's experts in the field. And it's a tough nut to crack, to comprehend, and to analyze and to use effectively. But nevertheless, it is a mode of moving heat. The best analogy I can give for radiation exchanging heat, if you stand near a fireplace and you're far enough away, say it's across the room, but you can still feel the heat on your face, or if you've ever witnessed like a pyrotechnic show where they're exploding fireworks and whatever, and you feel the heat from a large flame, but you're not close enough where it's the convection or the heating of the air, you're actually feeling the radiation heat on your body. So that's an example of radiation heat transfer. More commonly, though, that we're going to use are the modes of conduction and convection. Conduction, you're moving heat through a solid object, and it's basically the vibration of the atoms within the solid and the movement of electrons that are moving heat from one part of the solid to the other. And here's an example. We're heating up the end of a rod with a gas flame, and the heat's moving along. And then convection, it's the motion of the medium, so it's usually a liquid or gas, that's picking up the heat, and due to buoyancy forces or maybe a forced flow by a pump or a fan, that heated gas or liquids being pushed away from the heated surface and depositing that heat at a cooler area. And here's just an example of a burner and a pool of liquid, and obviously the water or liquid in this case, it heats up, rises to the surface where some of the heat is carried away then from the air picks this up and convects it away, and then the liquid returns back down here cooled, where it gets heated back up and carries it up. Real basic stuff, right? Okay, conduction heat transfer. This is about as detailed into the mathematics where we're going to get in this course, but this is the what's called Fourier's 1D conduction law describes how heat transfers in one dimension in a solid object. And so the heat flow rate in watts, which is energy per unit time, is equal to this value K, which is thermal conductivity. It's a property of a solid substance to effectively transport heat through it. Multiplied by the area cross-sectional to the path of the heat flow, multiplied by the temperature difference between 2 points in the solid object, divided by the length of that path that you're going over, L. And this equation, this only describes heat in one dimension. This is actually a real valuable equation, and the next one down is even probably more valuable for the thermal engineer. All I've done here is this equation's been rewritten, where I've introduced this resistance term. The resistance is defined as L over Ka. That's the resistance to conduction heat transfer, where L is the path length, K is the thermal conductivity, the property of the material, and A is the cross-sectional area that the energy is passing through. So obviously, as my path length increases, what happens to my thermal resistance? It's going to increase. It's pretty intuitive from this equation. So if my heat sink is at this end of the table, but my heat generating device is way down here. As the table gets longer and longer, I'm putting more material in between, and it's harder and harder to get the heat from here to here. And so my resistance is going up. Likewise, the cross-sectional area, the more area I have, the resistance goes down. If I constrict the area, the resistance goes up. And the other knob I have to turn there is the thermal conductivity. So why do we see heat sinks in computers made out of aluminum?
Property of the aluminum.
Yes, it's thermal conductivity. It's a good mover of heat. If you made it out of styrofoam, it probably wouldn't work very well. And that's because styrofoam has actually a very low thermal conductivity. And so the K value is very low for that. So playing around with those parameters, you can change thermal resistance. And so this is a very simplistic equation that you can use for just doing a simple assessment. Let's say you're trying to determine where to place the power supply in a chassis. And you've got it on a heat sink. You're just trying to figure out, well, what kind of gain do I get if I take the power supply and move it from this corner of the box, maybe to the center? Or maybe that's a decrease in performance because now, if the heat's got to go to the outside of the box, I move the power supply to the middle. I've increased the path length. So if I want to dump the heat to keep the same thermal resistance, maybe I've got to look at a heat sink with a different thermal conductivity or a different area. So having a simple equation like this, you can do some quick back-of-the-envelope calculations without having to run a computer code, without building a test. This is a simple tool, and I use this all the time. You know, sometimes I wonder why I even stayed in college to get a PhD. I'm like, I learned a lot of stuff I don't use. It's the simple stuff that that provides some of the most useful information for me. So these simple equations, they go a long way, and I'll show you how to. If you're not familiar with them, we'll talk later about building nodal networks, which they look like electrical diagrams where you construct a series of thermal resistors between parts in your system, and you can dump in these resistances into these nodal networks and quickly do a hand calculation at your desk to come up with a concept for a thermal design. I do this all the time, and it's a real effective technique. So that was conduction. Here's the equation for convection heat transfer. And in this case, so note we talk about convection heat transfer rate, which is Q. That's in watts or BT, the English units. So the units on Q can either be watts, which is a joule per second, or the English units are BTUs per hour. And then we talk about a thing called heat flux, and it's consistently noted with a double prime. What it means is it's the heat rate Q divided by an area. So it's, in this case, it would be watts. In the metric system, it would be watts per square meter, for example. Anyway, that heat flux is related to the, this is the equation to represent convection heat transfer, the movement of energy from a solid object into a fluid. And it's just like the conduction equation before, we have this parameter, and in this case, in the convection world, we use H. And H is called the film coefficient or heat transfer coefficient. It describes the effectiveness of moving heat from the solid to the fluid. And then, of course, we have the temperature difference that drives that. And the temperature difference is the temperature of the solid and the temperature of the fluid medium well away from the surface. And so that film coefficient is dependent on geometry, it's dependent on the type of fluid. It's usually something that's experimentally measured, and there are equations to predict what those values should be. And when we get into chapter 4, I'll show you a lot of those equations that you can use to calculate that film coefficient. But just like the conduction equation, the convection equation is pretty simplistic. This is for one-dimensional heat transfer, and we'll go into that more in a later chapter. But yeah, there's the same equation written down. Just some things to note. Water, liquids, they tend to have higher heat transfer coefficients for a given geometry than, say, a gaseous medium. So here's just a comparison between air and oil for one particular application. And heat transfer coefficients in this case for a particular flow of air was on the order of 12 to 17 BTUs per hour per foot squared degree F, and they're an order of magnitude higher for oil. So liquids tend to be a better mover of heat in convection than gases. But they have their associated problems, obviously, with look at the cost involved in using a water cooling system versus a simple fan blowing air. Okay, here's just some measures of heat fluxes. So again, heat flux is it's power per square area, or per unit area, and we're designating that Q double prime. And this is just kind of an interesting chart to give you an idea of how much heat flux we're pushing with some of our semiconductor devices, and those are shown right here. Relative, and laser diodes shown right above it, relative to these different events. So solar heating, rocket motor cases, how much heat flows going through the outside of a rocket motor case, a nuclear blast. I guess it's 1 mile away for a 1 megaton blast. Kind of funny to try to compare, but it gives you an idea that we're pushing a lot of heat in our electronics at 10 to 100 watts per square centimeter. It's a lot of energy per unit time going through a small area. And this graph just tries to compare the two events. Of course, these are happening at much higher temperatures, obviously. We don't want our semiconductors operating at thousands of Kelvin, be melting and dripping through the bottom of your computer cabinet. Okay, just some examples of heat transfer methods in electronic cooling. So in the upper left is an example of natural convection. Again, convection is the movement of fluid, right? And so this is just an example where this is a computer prediction showing, those are actually arrows showing airflow, and then the color of the arrow is associated with the temperature, where the blue is the cooling air coming in, and then the yellow, red, and green is the hot air being carried away from the heated surface right here. So free convection, natural convection, that's a freebie. A lot of our devices operate off of that principle. Your cell phones rely on free convection from the surface of the phone to dump the heat to the environment. There's no fans running on your cell phone, thank goodness. And then when things get a little bit tougher, we've got to rely on what's called forced convection. Forced convection is where we're purposely pushing the fluid, and you're familiar with these. So here's an example of a fan sitting on top of a heatsink, purposely pushing air to cool the electronics. Then there are, here's an example of an evaporator convection device put on top of some processors. So this is, we'll talk about what heat pipes are in our advanced cooling section, but basically they're a closed system that has a liquid that evaporates from the heat, that vapor travels down the length of the heat pipe and condenses at the cold end and dumps the heat at that end, and it's carried away by another technique or method. But this shows this is an evaporator system with heat pipes that go down to a condenser body down below. and these are to move even more heat than convection techniques shown in the previous two pictures. Here's down below, this is what's called an indirect and a direct immersion, where simulated computer chips are either separated from the cooling medium indirectly. There's some barrier, but they're moving their heat by conduction and then convection into the cooling medium. Or there are these dielectric liquids, and we'll talk about those in more detail in the advanced cooling section, cooling applications chapter, where the chips can actually be immersed in this fluid. It doesn't conduct electricity, and the liquid will actually not disrupt the electrical circuit, but it puts the dielectric liquid right in contact with the components and carry the heat away. And then we can take that a step further, and we can actually boil that fluid and pull even more heat away. This is it. Now we're starting to get into the Ferraris of cooling techniques. These are the high-end, high-performance techniques. You like to try to operate down here, and as your designs and things get more complex, you progress through these different cooling techniques. For some of those things shown in that previous slide, here are the different cooling techniques. And what's shown here is, this is just to give you a rough comparison of how one technique compares to another. And what's plotted here is temperature difference. This is, say, the temperature of your device versus the temperature of your cooling medium versus heat flux, watts per square centimeter. So down here we have the cheap, easy techniques, the natural convection, then we go to forced convection, immersion with liquids, and then these things called microchannel heat exchangers, where it's a small heat exchanger with really tiny holes in it, and you're pumping water through it at extremely high pressures and high flow rates. You can see that if I were to pick, let's say I only wanted a temperature difference of 10 degrees C, based on my heat flux, it would dictate what technique I probably need to consider. If I'm looking at pushing 100 watts per square centimeter, I'm probably not going to be able to use anything with natural or forced air convection. I'm down here. Actually, some of these techniques, there's a lot that aren't listed here, but some of these techniques would spill over, and I could probably use something out here. But this chart's a value. It just shows the relative comparison of these techniques. And there's some text that describes that. So again, just an overview. What are the general steps to a thermal design process? You might be involved in just one portion of this, but this is the general. In an ideal world, if thermal design is important to a particular product and it's adequately funded and provided for, you start off with deciding what are the system requirements. This gets left out so frequently. People don't understand necessarily what temperature they want to run at, what are the environmental conditions. Is it going to be in the desert? Is it just going to be inside a temperature controlled building? What cooling availability do I have? Do I got to run off battery power? Can I run a cooling system off 120 volt? Does the customer mind if they have a fan on their cell phone? What do you want? Yeah, so defining system requirements up front is so important for the thermal designer to know what techniques to use, what temperatures they should be striving for. What kind of reliability do you want out of this? Is this a device that's going to be used for a year, or is it going to be 10 years? Generally, the circuit is designed. The electrical almost always leads the mechanical. The electrical engineers are deciding on their schematics, their layouts, their component selections, and then from that has to come the heat flux calculations, figuring out how much power these things are using. Again, that may be some mechanical, but it's primarily in these early stages being driven by the electrical team. They're developing their layouts, but it's at this point that the thermal analysis needs to start being thought about and prepared for, because depending on how the electrical circuits and electrical systems are laid out may limit your cooling techniques and your strategies that you use. And it isn't until you actually do some thermal analyses that you figure out what works and what doesn't. But it's in here that the thermal analysis and thermal design gets put into a loop right here, where you're working on doing different analyses. Maybe you're building a prototype, but most often you're trying to do hand calculations, some simple analyses, figure out what works for the design. Once you've got something you're happy with, you move into prototype or production, you build it and you test it. And if it turns out it didn't work, your analysis was wrong, somebody changed their requirements, you may have to step back into this process. But your goal is to get here and have done this, and this, and this along the way. All right, and this is just a regurgitation of what we talked about: energy, being force and resistance. I just want you to remember that, there's analogies with Ohm's law and electricity. We're going to use the same thing in the flow of heat, and this equation we're going to use to build these thermal networks to analyze a system, to show how heat moves through it. It's a real good back of the envelope hand calculation type strategy. A little bit more basic information. Equipment design approaches. So we showed some pictures of different cooling techniques, and this chart just tries to summarize the cost impacts of these. So starting with ambient air cooling, natural convection, those are your cheapest alternatives, and as you go down, the costs go up. We'll talk more about these. I'll show you plenty of examples when we get into chapters 7, 8, and such. Just kind of a checklist. These are some of the basis for thermal design decisions. What the customer needs, what the requirements and specs are. Renee, you were talking about how someone comes in and says, I need this. And so the customer in this case is dictating what their needs are, and that'll drive your cooling strategies. Quantity of heat, obviously, your part temperature limits, what they're capable of doing. Cost. Obviously, the higher Cadillac cooling systems, thermal management systems, can drive up the cost, can make things more reliable, but in today's environment, being competitive and cost is sometimes king. Surrounding environment, what type of temperatures, cooling environments you have to work from. Certainly designing a device to go in a submarine, your cooling resources are much more limited than, say, a surface ship. And so knowing your surrounding environment, where your heat sinks are, where you can dump your heat to, and what modes you can use to do that, play a big role. Physical size limitations, what cooling methods you have available. You guys are used to using certain commercial type techniques in the products that you use, and so you probably have a good idea on what methods are available or what you have been using. But there may be some advanced techniques that we'll discuss in the next few days. And startup requirements. How quickly does this thing have to integrate and work? So again, looking at the big picture, there's a lot of things involved in selecting and designing a cooling system that you may or may not be aware of. Some more text on things to think about as we move ahead here with the design and analysis.